Session, we're going to move on to how PSyclone supports distributed memory for LFRic and how it makes use of the infrastructure to do that. It builds on previous things that previous people have talked about already, so hopefully it won't all be completely new to you. This is going to be a 90-minute session. We're going to jump straight in on a hands-on to start off with, called Going Parallel. Which should just take about 15 minutes, and then we're going to I'm going to give an introduction kind of to the underlying support for distributed memory, hopefully about 30 minutes, and then we're going to move on to the second set of hands-ons. Okay, so we're going to jump straight in. So sorry to you people who are continuing doing the previous session. If you could now go to the tutorial practicals LFRic distributed memory 1 _ distributed memory directory. In this case, we're not going to be doing any compilation, it's just code generation. I don't think you need to use any make files. It'll just be PSyclone command line stuff. Whether that's a good or bad thing, I guess we'll find out. So please, as usual, follow the README in that directory. The best way to do that is to use a browser. You can look at it directly if you want to, but it looks nicer in a browser. And you can go to GitHub to do that. I guess most of you are doing that already. And as usual, again, any questions, issues on Slack, but we're also monitoring the Google Docs as well if you want to put anything on there. So either of those is fine. So have fun, and we'll talk to you on Slack, and we'll carry on presenting in about 15 minutes. If you haven't completed it yet, don't worry, you can continue after the presentation. It's not a problem, it's not a race or anything, even though Sebastian managed to win the virtual cookie. Okay, so we're going to carry on. I'm going to spend hopefully about, well, at most 30 minutes on how we go parallel. So just, here we go. Yes, so just a summary of what this is. Hopefully, I mean, you should have got this information anyway. The code you've looked at is an example code extracted from LFRic. It's actually the most computationally costly part of the dynamical core, so it's quite an important part of the code. There is a sneaky change in there, which if you didn't notice, anyone notices, feel free to put it on Slack. There's a challenge for you, and I'll explain why. It's actually not needed for this tutorial, but it's there anyway. So the point is, I think, is that when you went parallel, you went from serial to parallel. It's the same algorithm and kernel code that was written by the scientist was used to run both of these, either serially or in parallel. That didn't change. So this gives us single source science code. And the second thing is that the science code itself was not concerned with the parallel implementation at all. That was kept in the generated Sci layer. So the take home is, from a user's perspective, generating serial or distributed memory parallel code is essentially controlled by a single PSyclone command line argument, the no DM or the -dm. That's the take home. And in practice, so you know this isn't kind of just a theoretical thing, PSyclone was integrated into the LFRic build system way back in September 2015, and at that time it was serial. And then in March 2016, we went parallel with actually not just MPI, with MPI and OpenMP, but for the purposes of the moment, let's just think about MPI. And that switch was essentially immediate. So it was just this equivalent of what you've just done. We went from the no DM to the DM option. But actually it took 1 week in practice due to a bug in productions, which actually was my fault. Again, if you're interested in knowing what that was, you can ask the question somewhere, and I'll explain why I was an idiot and how to fix it. It was quite a simple thing. So that's why it took a little while to validate. But the point is when they went from running in serial to parallel, there was no change to the science code. That's just a switch in the build system, and it was all done behind the scenes by PSyclone and the support in the LFRic infrastructure. So the science code didn't change at all. And just to show you, can I do a pointer? Yeah. So up here, probably at the time was very exciting, but this was some results running in serial, I think, on the right-hand side, and then the equivalent results running in parallel. The first results we got, and obviously you can see they're the same, which was very exciting then, but not the prettiest of pictures now, but still quite an important point for us. And the other point is that since we went parallel, science development has continued since then, and the code's got more and more complicated, and this is kind of a Met-Office timeline in terms of the how the code's getting more and more complicated, ready to eventually go operational. And they've continued to use PSyclone and continued to not worry about parallelism, and continue to develop in the same way that Eva talked about, and that's just been there, and the separation of concerns in practice is actually working, in my opinion. So we're now going to talk about how parallelism is implemented, and sort of explain some of the things you saw in that first tutorial. So as you probably know, the implementation at the moment is a cube sphere, and in the middle here is my representation of a simple part of a cube sphere, so we can just sort of see what's going on in a simple way. And think of these things, whilst of course it looks like it's two-dimensional wrapped around the world, there are columns, so these are cell columns, but I'm just going to keep it like this for simplicity. And when you go parallel, what you do is you partition up your cells into different processes, and then they can work on things independently. So it's typical domain decomposition. I guess most of you know about this sort of stuff. So it's quite a simple concept. So let's look at degrees of freedom for a discontinuous function space. So Eva's brought up, explained discontinuous and continuous function spaces before, but from PSyclone's perspective, a discontinuous function space is just something where the degrees of freedom are within the cell. There's no sharing between cells of degrees of freedom. And I think this example is a lowest order W3 field, I believe. So anyway, so the point is that they're inside the cell, and there are two modes of iterating over these things. Two types of loops you'll get is one when we go from 1 to the number of degrees of freedom. That essentially means going over each of these green things one at a time, and computing them. And of course, remember that they're coming out. That there's not just one here. This is a column of cells, so you're also doing a column, and you can do those in any order, and you just go from 1 to number of DOS, and that's what we do for built-in codes. And the access patterns you'll see for those is you either read them, write them, or you read-write them, and you'll see that in the metadata. You can also iterate over cells. So rather than iterating over the DOS and cells, you iterate over cells, and that's where you do columns. And so that's why you call a kernel. Inside the kernel, you do the column. And again, the accesses in this case are read, write, and read-write in the kernel metadata. So that's how we think about it. So if we partition these things in parallel, well, life's quite simple because they're all independent. There's nothing in between them. So as long as the infrastructure gives PSyclone the right number for NDOFs, so NDOFs now, rather than being across the whole thing, it's now just a local one. So if your MPI are in this area, you'll just have an NDOS for these. Your MPI on this one, you'll have NDOS for these. So as long as these things are changed for built-in codes, and this thing is changed for going over cells, and there's a renumbering that's sorted out by the infrastructure, then essentially for PSyclone's perspective, it's very little difference. So it's quite easy for PSyclone to be able to continue to do distributed memory for this. Now let's think about continuous function spaces. So this is you can see they're on the vertices. I think this is an example of a lowest order W0. That's fine. That's a standard thing you might want to do. So let's iterate over DOFs. Well, again, you can just iterate over DOFs as normal in any order that is appropriate, and you can read, write, and read, write those. That's fine. But Now this is the kind of the issue is when you iterate over cells. Now let's just take this one because this is an example. So if we're in this one, then we're going to contribute to this one, to this one, to this one, and this one. But if we're in this cell, we're going to contribute to this one, this one, this one, and this one. And you can see here as the example is that this cell will contribute to this one, so will this, so will this, so will this. So now when we iterate over cells and we go in parallel, we're not independent. So you can't do these things completely in parallel. You've got to do some sort of mechanism to cope with the fact that these things are going to be updated together. And that's why in the metadata you'll see for these types of kernels, when you're iterating over cells and it's a continuous function space, you won't see read write, you'll see inc. And that's what tells Cyclone that this is a different thing and it needs to do something differently. So let's partition this. So now we have the issue that we had these things on the edges, and now we've kind of pulled them apart. There are replicas of them. So this one is here and here, and in our little corner case, so this one is here, and there's a replica here, here, and here. It's okay that, and in fact, what we call these things annexed. That's the name for annexed. You've heard of annexed. That's what these things are. So we decide there's an owner. We say, okay, well, we're going to say this one owns this one, and then these ones are going to be copies, and they're the annexed ones. Now, iterating over DOFs, from Cyclone's perspective, if we decide to just go from have a scheme where we just have a layout where the own DOFs are first in a space and annexed DOFs are afterwards, then we can still just go from 1 to n DOFs, and everything is fine from our perspective. You can just iterate over those, the owned ones, and everything is fine. And then, of course, you need to worry about updating these ones. If you need to read the ones that are copies at some point, you need to update them at some point. Let's not worry about it for the moment. But now, let's think about iterating over cells. Well, what we could do is we could just iterate over cells as normal, and let's see what happens on the edges. So in this case, this one contributes to this one contributes to this one contributes to this, and this one contributes to this. So these things, the copies and the original, are essentially partial sums. So you could, in theory, you could just compute over cells as normal, and then when you wanted to maybe have the correct value in these other ones, in all of them, in fact, you could then do some sort of communication which also did a sum of these things, the partial sums, and then copied all the values across. So you could do that. So you could iterate over cells and do that. That is an option. But as you can see from the big red X, that's not what we do. What we do is this. So what we do is we do redundant computation. So now we've got halo cells around the edges, as you can see, around all these edges here, which are copies of the neighbors. And what we do is, if we're going for continuous function space and we have this inc, then we actually go from 1 to the cell halo. That means we do all of these, and we also go on to the halos as well. We compute the halos as well. Now, the advantage of computing the halos is that you can see here, if we want to get this value, then because we're computing in the halos, we actually get it from all of these contributions. So at the end of this, all of the green ones are correct. And we also, on the other ones, even if not the owned ones, we also get contributions from everywhere. So all of the green and the yellow, the annexed DOFs, are also correct. So after we do this, we end up with all the green and the yellow all correct on all different processes. What we don't do is the red ones end up being incorrect. Okay, so in kind of simple terms, we end up with all the owned DOFs and the annexed DOFs all end up being correct, but the halos end up being incorrect. And you can just see, just to simplify things, the scheme that we go through to make things easy for going over DOFs is 1 to DOFs, and then annexed DOFs, and then halo DOFs. You only see depth 1 at the moment, but we do support depths of 2, 3, and 4 for redundant computation. And similar thing for owned cells. To make life easy, we go from 1 to owned to the number of cells first, and then the halo cells are added in terms of the numbering afterwards. So that just means we can just do iteration spaces of 1 to cells, or 1 to n cells, or sorry, cell halo, and we get all of them. So in this case, we're going just from 1 to cell halo 1. That'll get all the internal ones and the halo ones as well. Okay. So hopefully you would have seen this this output when you did the previous tutorial, and you would have seen that that what's been added are these halo exchanges. Okay, there's 4 added here and 1 added here. So how do we do that? Some people think it's magic. It certainly isn't. It just uses the logic. Okay, so we're going to just go through a couple of these just to see what happens. So this is what the algorithm does in order to place halo exchanges. There's internal inside Cyclone. So what it does is it looks at loop 1. Okay, so loop 1 is here, and then it's a built-in setting grad p to 0, and it goes from 1 to end offs. There you can see end offs, and it's writing to grad p. So when you write to grad p, you're making the halo doffs dirty because any copies are now out of date. You're also making the annex doffs dirty because we're only writing to the number of doffs, not going to the annex doffs. So both all the halo doffs and the annex doffs are dirty after this loop. But we don't read anything here. We're only writing to things. So we don't need a halo exchange because we're just writing. So we can move on. We've got that information, so we move on to the next step. Okay, so let's look at loop 2. So here's loop 2, and we've got our scale matrix vector code. I'm afraid it's obviously, you can't see the rest of it at the moment. Now in loop 2, we're modifying grad p, that's this thing here, which you can't quite see. And if you look to the metadata, it's unclear whether it's continuous or not. So we have to assume that it is continuous. Otherwise, if we don't, if it is continuous, we get the wrong results. So if you don't know, you have to assume it's continuous. So you iterate to the cell halo. So if you go from 1 to cell halo, what that does for grad p is it makes the halo doffs dirty, like I said before. But if you remember, it'll make the annex doffs clean. But in order to do the annex doffs, it actually needs the annex doffs to be clean already. And the problem is that previous loop, if you remember, made them dirty. So because of that, we need to update our annex doffs. Now there's no update of annex doffs direct in LFRic, so we just do a full halo exchange at this point, and that's what this halo exchange is here, saying I need to do that. So that's why Cyclone puts it in. And you notice it says check dirty is false. That's because it knows that from this loop to this loop, we need a halo exchange in there no matter what. So that's why it puts it in there. Okay, we'll just do one more, which is the other arguments to this scale metric vector code. So we're updating grad p. We're also reading p, div star, and hbinf. Those things are read. You can see that in the metadata in the kernel. Now, as we're iterating from 1 to cell halo, and we're reading them, those things must have the values in their halos correct. So if they don't, we're going to get incorrect results. So what we say is that we don't actually know. If you go backwards from here, there's no information about what's happened to p, div star, and hbinf before this. So it happens outside of the invoke beforehand. So what we do is we say, well, okay, we're going to put a speculative halo exchange in here for these things, and we're going to say, please check whether or not we need the halo exchange. So it's a runtime check which says, do we need it? If we do it. Okay. And I think next we're going to look at some code. So this is generated code, and so you've probably seen this as well. So this is that first loop up here, and you'll see what we do is we actually have runtime flags which we set. So Cyclone adds these in so that it keeps a kind of information about what's clean and what's dirty, and that's how it works it out. So here, for example, after this, if you remember, we made things dirty, so it says set this to dirty. And we know we needed a halo exchange. That's one where we know we needed a halo exchange. And then these ones are speculative. We don't know. So we basically say, if it is dirty, then do the halo exchange. If this is dirty, do the halo exchange. So these may not happen, depending whether it's dirty or not. And then finally, after this, we're writing to grad p proxy here. And if you remember, the halos end up being dirty at the end. So we had to put a set dirty there. And if that's done throughout the code, then we keep information between invokes, runtime information. So the information comes in and it's always up to date. So we can then keep track of what's dirty and what's clean, and then these halo exchanges work. So that's how it's done. So I'm just going to go through some of the optimizations that you're going to be looking at. So one of them is called annexdot. Okay, so as we said before, LFRic either loops over cells or dots at the moment. Now, if we iterate over the cells, if you remember, hopefully, that we always guarantee that those annex dots for a continuous field are going to be clean, because we do the redundant computation. When we do the redundant computation, so the owned and annex dots are always clean. So if we iterate over cells, they're always going to be clean. So annex dots are always clean. So why not redundantly compute annex dots when we iterate over dots? And if we do that, there should be no additional halo exchanges. But we have seen in example one, that first example, one of them, that if we have annex dots that are dirty, they can result in additional halo exchanges. So if we redundantly compute annex dots for the whole code, then we can actually assume that annex dots are always clean. And that could potentially reduce the number of halo exchanges. And that's what this annex dot optimization does. And you're going to see that in the tutorial. So the change is essentially simple. Because of this numbering scheme, to do it redundantly, rather than going from 1 to n dots, you go from 1 to an annexed, and that does those as well. So here, beforehand, we were just doing all the green ones, and now we're going to do the green ones and those ones as well. So that's the change. So from a Cyclone's perspective, because of the layout, it's relatively easy. What does this do? So this is an early version of LFRic called fallowdia, and this was a count of the number of halo exchanges that actually took place in the run. So it counted, did you do a halo exchange, and count them up. Now I'm not going to talk about this other optimization. That's an internal thing, but combined with these things together, with this annex DOS, was a significant reduction in the number of halo exchanges. So you could argue we should always have that in. That is now in LFRic by default as of the last release, this optimization. Okay, so that's a way of trying to get rid of halo exchanges. What happens if you can't get rid of them? What else can you do? Well, you can try and avoid them. So one way to try and, if you can't avoid them, you try and overlap them, apologies. Because if you can overlap them, then you can, it means that the cost of the halo exchange can be reduced or got rid of completely because you're computing at the same time. So Cyclone provides a couple of transformations to help with this, which we're going to play with in a bit. One of them which changes the synchronous halo exchange into an asynchronous one. And you'll see how that's done. Essentially, it's just changing the calls because the infrastructure supports it. And then another transformation, because if you just change from synchronous to asynchronous, it's not going to help you because you've got no overlap. There's a second transformation that is a generic one that moves IR nodes around. And in this case, we can pull backwards the start of the asynchronous halo exchange to do some overlapping with computation. And you'll see how we do that in the example. So in general, LFRic and Cyclone within LFRic supports two types of communication patterns. One is a nearest neighbor stencil communication pattern, which makes use of the halo exchanges we've seen. We're not going to see any examples of that, but Cyclone does support it. There is metadata to support stencils, as you'd expect. And it does the right thing for those. Like I said, there's not, we haven't gotten a tutorial because that's kind of beyond where we can do it. I mean, it's all working, but there's not enough time to show those. The other thing that we can do and support is reductions. So the summation reduction is very simple. You basically have some data in an array and you want to reduce it down to a scalar. And of course, the problem is that if you're doing this in distributed memory, you're going to get local values of A, not global ones, and then you need to somehow to reduce those down and get global values. So you end up with a global sum of some sort, and you'll see how that's supported. Quickly go through what else. We also do support arbitrary depth redundant computation. There's a transformation to do that, but we're not going to show you that for the moment. And it's not really used, but it is there and can be played about with. And in the future, there's a number of things that we're going to look at. In particular, we like to do loop splitting. We don't do that at the moment. That allows more overlap between asynchronous halo exchanges. Potentially communication aggregation, so you could put halo exchanges together and do one larger halo exchange. And there's a few other things which, if you're interested, I can talk about maybe on Slack. But they're kind of more speculative things. Now, if there are any other things, any optimizations that anyone who's out there who's an expert can think of that might help, please let me know, because I think we've kind of covered everything. But if not, I'd be very interested to know if there's any other things we could do. Okay, so I've given a quick overview. The rest of this session is going to be hands-on again. There are 3 parts. You've done the first one underscore in the distributed memory. Part of this, and now there's 2 annexdots, 3 overlapping comms, and 4 reductions. Those three things I talked about. Again, there's no compilation, it's just code generation, and as usual, there's readmes in each of these directories. Now, I don't think you're going to have enough time to do all of these in 45 minutes. If you do, well done. You can get a cookie, but feel free to carry on over anytime you like. We will be around, and just get as far as you can, and feel free to do these in, I think you can do them in any order. I don't think there's an ordering, so if you prefer to do one before the other, it's fine. Okay, so have fun, and we'll talk on Slack. Thank you very much.